This week we're going to be studying trees. So much of this work is due to a landmark book that was published in 1984. I proudly show you my copy of this book. It's called the CART book. So CART stands for Classification and Regression Trees. And the authors are Leo Breiman, Jerry Friedman, Olshan, and Stone. I'll just show the Google Scholar page for a second. When you have an article that gets 10 sites, that's a pretty good article. If you get 100 sites, that's a pretty major article. If you have 1,000, that's a very, very important article. Well, this book has accumulated over 45,000 sites, so it's one of the most influential texts in all of machine learning. All right, well, to get us into this subject, I'd like to kind of step back and review some of the things that we did last week. So what we did was we talked about smoothing. And so let me just refresh your memory of how smoothing works. So we started out in one dimension, and maybe we had a whole bunch of data points like this, and let's let it flatten out a little bit. And so then the idea of smoothing is you want to do some sort of local averaging to estimate the regression function. So there's a true regression function that passes through the middle of the data. So this is f at x. And we want to do some sort of local fitting in order to estimate this f. And so we tried a couple different ways. One way is we used a bin smoother. So we created some bins, and then we average all of the y values. So take the average of all the y values in this bin, which you could also think of as like a neighborhood, but it's a fixed neighborhood. And so this would be the predicted value for all the observations in this first bin. We would then average all of these points and average all of these points to get our estimate of f, which in this case would be a step function. We did some other things, like we looked at, instead of having these fixed bins, I could have a moving bin. So we called that a nearest neighbor smoother. Or we also looked at fitting more complicated functions in each bin. So instead of having this piecewise constant model, you could fit piecewise lines or piecewise cubic polynomials. All right, well, why don't we just do this if we have more than one predictor? So often we have many predictors. So what to do in the case of p predictors? Well, there's a problem that we're going to run into if we try to do this local averaging, and that problem is called the Curse of Dimensionality. So to kind of give you a sense for the problem here, let's say now that we have p equal to 2 predictors. Up here we just had p equal to 1 predictor, and so maybe this is my scatter plot. I have the x1 axis here, I have the x2 axis here, and my y-axis is coming out of the page where this pen is. All right, so maybe I have a bunch of points out here, and then their corresponding heights. And so let's just do the same thing. I'm going to go make myself some bins. So if I chop x1, say twice, as I did up here, and I cross this with 2 chops of my x2 variable, what I want you to notice is that I now have 9 bins. So I'm really fragmenting my data quite quickly. If I took this up to p equal to 3, I would have 27 bins. What would happen if I had, p equal to 10 is not at all a small problem. We commonly would have that many. If you look at 3 to the 10th, you're at about 59,000 bins. Okay, so if I had 59,000 bins with only 10 variables, and I'm going to compute the average in each of those bins, then what's going to happen is the function is going to be very unreliable. because I just don't have enough data unless I have an absolutely massive data set. And so we cracked finding an automatic method in one dimension through these simple local averages, but it's not going to work when we have high dimensions. So what the Curse of Dimensionality says is that even if you have very large data sets, if you start making a lot of bins, the data set is going to be very sparse in these high dimensional spaces. So what do? Well, a number of approaches have been proposed in machine learning, and the method that we're going to study today is the method that Breiman and Friedman really developed this approach back in the late 70s and early 80s, called recursive partitioning. And so the idea of recursive partitioning of the domain is that we're going to build a bin smoother. So that's why it took us through the bin smoother again. But we're only going to introduce splits when we need them and when we can support them. Okay, so rather than just a priori, having two chops here, maybe I did them at the tri-tiles, we're going to be very selective in when we allow ourselves to have a cut. And so, two things that we're going to be considering will be, is the function changing? So do I really need another split here? Because the function's quite constant out here. So maybe I don't really need to spend a degree of freedom when my function is completely flat. So we have much more of a change in the function down here. The function is changing very rapidly, and this is where we would want to be spending more of our degrees of freedom to capture that curve. Well, another consideration is, do we have data to support a split? So if we go look at this two-dimensional one, notice I don't have any data points up in this corner. Maybe I shouldn't be introducing this extra split, and maybe I should just have, maybe a block like this, or even a bigger block. I can only split where there's data. All right, so that's going to be the idea that we're going to follow with recursive partitioning. And so, namely, only introduce splits when you can support them and when you need them because the function is changing. So I'm going to introduce some notation for us in order to describe this algorithm. Maybe my notation is a little too complicated. I hope you don't find it too complicated, though. So I'm going to assume the usual starting point where I've got a continuous function over p variables, and I've observed n data points that I want to use to create an estimate of this f. I'm going to use the script, the script font to indicate sets of observations, and we'll index those observations through the observation number. So, for example, I'm going to start out with all my data points, so this would be 1 through n. So that's going to be my entire data set. Now, the idea is we're going to create some sort of a split, and so d sub k will be if you think of this as bin number k, and this dk is going to be some subset of my observations, and then we'll have corresponding measures on that bin. So n sub k is just going to be the number of cases. We're going to have y bar sub k is just going to be the mean, the bin mean of that, and then RSS is going to be what we've left out. So what is the error associated with that? So just to make this a little bit more concrete, I'm going to go make myself a scatterplot, and let's stay in one dimension where things are a little bit familiar, and I'm going to give myself not a whole lot of data points. So maybe a version of this function that flattens out, but not with as many data points. All right, I'm going to say that this is observation 1, 2, 3, 4, 5, 6, and 7. And then let's say I had some sort of a split. So my algorithm found that we need to split my x right here. And so we could call this, bin 1. We're going to call this a node in a tree in just a second. And this is going to be bin 2. So what we would have in terms of my notation is my script D will be all observations, so 1, 2 through 7. D1, which is going to be the set of observations falling in the first bin, will be 1, 2, 3, and 4. And then D2 is going to be the remaining observations, 5, 6, and 7. So notice that my D is equal to D1 union D2, and my D1 and D2 are mutually exclusive. So D1 intersect D2 equals the empty set. All right. So that's what I mean by these Ds. Now we could also say that N1 is equal to 4 data points, N2 is equal to 3 data points, and the sum of these equals 7. Well, what is the bin smoother? Well, the bin smoother would be this. Well, y bar 1 would be the sum. Well, let me just write it like this. y1 plus y2 plus y3 plus y4 divided by 4, and we've done our local averaging. So let me just write on my graph what this y bar 1 is. So it's just we're just doing bin smoothing over again, except I was very clever in the way I chose this split point because I used an algorithm that I'll describe in a second to find that split point. And then y bar 2 would be, well, y5 plus y6 plus y7 divided by 3. And so I think that mean is about here. So that would be y bar 2. All right, well, the next thing we need to know is how much information have I lost in going from the raw data to my mean. My mean here is this, the fitted model is this mean. And so the way we're going to summarize this is the way we always summarize what's left out. I'm going to make myself some residuals. And so let's go make ourselves some residuals here as well. And so I'm going to define a quantity RSS K, which is going to be the sum of all observations in that subset of y sub I minus y bar K squared. So, we could write this out for, let's just do it for the second one because that one's a little bit easier. This would just be, well, how far is y5 from y bar 2? So that's this line right here, squared, plus, well, y6 minus y bar 2 squared plus y7 minus y bar 2 squared. And so that would be the amount of information that I've lost by going from the raw data to this model. So that's what these RSSs are all about. Now, let's go back to my course packet here. The way we're going to choose this split, so think of DK in this case as my entire data set, and I split it up into, you can think of this as a left bin and a right bin. We're going to call it the left child of a tree of a parent node and the right node of a parent node. The way we're going to choose this is in a greedy fashion, very similar to forward selection. So remember what forward selection was? We're going to go see which variable I could bring into the database, into my model, to improve the sums of squares as much as possible. That's what forward selection was. Well, I want to do the same thing with this tree model, except that rather than bringing a variable in right now, I want to bring a split in. Now, if I had more than one variable, I would search out every variable in every split in order to determine which one is going to give me the biggest improvement in RSS. But since I only have one variable, I would have to search each one of these 6 possible split points in this tree, and I'm going to choose the one that would give me the greatest improvement to RSS. So what exactly is this improvement to RSS? Well, we're going to take the starting bin, if you will, and compute what the error is with that, and then we're going to simply subtract off what is the error of the two split bins, right? So the left child and the right child, what are the errors associated with those two? And I'd like to make that improvement as much as possible. So let's just go back to my picture here. And if I consider just y bar, so y bar would be the whole data set. So we can think of this as y1 plus all the way through y7 divided by 7. This is going to be the model that looks like this. So it's going to be the grand average of all my y's, and I think it's about here. So this is y bar. Now, what I want to know is how much better is my fit versus the pink fit. So the pink fit here is RSS for not having a split. So RSS would be just the sum. Let me say j equals 1 to 7, or you could say j element of d. Y bar, yi minus y bar squared. And if I take RSS minus RSS1 minus RSS2, that's going to tell me how much better do these two lines fit than the pink line. And let me just point out that we've seen that pink line 100 times before in this class. Back in regression, we called this the Null Model. So if we assume that all of our slopes are 0, you just get the intercept, and that's that flat line. So we've kind of done this before, but not quite with the split. Okay, so what I've done is I've tried every possible split, and I've said, well, how much of an improvement is there in my RSS? So if I had split the data, say here, I'm going to go use a red pen, then what I would have is some line here and some point up here, and the RSS would not improve as much as when I did this particular split. Okay, so that's the core idea of bin smoothing, is we need to identify this split that's going to help me as much as possible, and we're doing that in a greedy way. So at a high level, this is the algorithm that we use to build a tree. So I have a function that I'm going to call recursively, and I'm going to pass to this function some data set. Now, the first thing the function is going to do is search for a split. So it's going to go through and try every possible split. If you have a big data set there, we may not want to try every split. We may want to be, we might want to introduce some computational tricks to avoid searching every split. But in a small data set like this, we could search every split. And I'm going to choose the one that maximizes the improvement in RSS. Now, once I found that split, I'm going to check some stopping criteria. So, for example, maybe I don't want to have some bins with fewer than 5 cases. In that case, I would exit. I would not introduce the split. Otherwise, I'm going to say we need that bin. We need this new split, giving us 2 additional bins. And I'm going to then recursively call this function on the observations in the left bin, and then after searching that, I do it for the right bin. So let's see how this works. I'm going to go over to this wave example. So remember we created a data set. Go back to my video on smoothing to get the exact function. This is a sine wave, and it's actually 3/4 of a period of a sine wave. And so I've generated, I think it was 30 data points, and we tried to estimate this with a bin smoother last week, and we actually got a very good answer when we used the spline. But let's take a look at this in the case of a tree. So how do you fit a tree in R? Well, there's a couple libraries that do it. One is the tree library. There's another library called rpart, so the letter R, P-A-R-T. We're going to use the tree library here. So tree takes a formula as does every other function, all of our modeling functions. Looks just like LM or GLM or GAM. So in this case, I would just say y tilde x, and I give the data set name. There is a built-in function called partition.tree that will produce a plot if you're in a lower dimensional, low dimensional p. And so in this case, I have one predictor variable, so p is 1, and it creates what is really just a bin smoother. So it's showing the bins that this tree model has found for us. And so if you think about what is this line right here, well, the answer is take the average of these 5 y values, and the average of those 5 y values would be this value. What is this line? Well, just average all these values. So it's, all we have here is a bin function, so it's like a step function, and that's it. Now, when you so I added the points with the points command just to show this. A couple other things. You can plot a fitted object from a tree, and you get this dendrogram down here to the right. Unfortunately, it doesn't put the labels on, so in order to get the labels, you have to use the text command. So you pass the fitted object to the text command, and it adds these labels for you to interpret the tree. If you use the deviance command, it gives you the RSS value for your final fit. So it's going to take the RSS for bin 1, bin 2, bin 3, bin 4, bin 5, add them up, and it's like the regression sums of squares back in regression. Now, if you were to take the sum of the observed y values minus their means squared, that's going to be the null model, right? So if I don't have any bins, if I just use a grand y bar, so that grand y bar is like that pink line that I had over here. Notice this is the residual sums of squares if I didn't give myself any splits. So notice there's a very dramatic improvement between having whatever I had there, 6 or 7 splits, and not having any. Finally, when you display a fitted object, you get a list of all the splits. So my goal right now is for you to be able to understand how this output is linked to this picture and to this dendrogram. This is called a dendrogram. So let's just start out with this fitted object. And so I'm going to maybe build the tree as I go over here. So let's just take X and Y. And here's what's going to happen. So we start out our tree with 30 observations. So that's the entire data set. And pay attention to the output up here. So that N is the 30. The deviance would be RSS. Okay, so the deviance for this X bar model is 17.46. Well, have we seen that number before? The answer is yes. 17.46 was what we found when we computed the basically the total sums of squares. It was another name we had for this because we just have one mean. And then the last value is going to be the average of all y's, so 0.1314. So think of this as a line going across, and that's the beginning model. So then what happened was R searched for the best possible split. So think of that function that I was showing you, build tree, and it said, well, if I introduce a split at 2.03, so let's see, 2.03 is about right here. So that's going to be my first split. My function is going to get better. Okay, so my residual sum of squares is going to reduce by a lot. So let's just go graph this. And so my first split over here is going to be at 2.03. And then you're going to see that of these 30 cases, 19 go to the left bin. So this is the left bin. This is the right bin. We can think of this as bin 2 and bin 3 if we follow R's labeling. So here's bin 2, here's bin 3. Notice we have 19 cases over here. So N2 is 19, and we have N3 equal to 11. All right. The fitted function would be y is equal to 0.66 for the left child. So y equals 0.66, and then y is equal to minus 0.78 for the right child. So y bar, we could write this y bar 2 if we want to use all my notation, minus 0.779, I guess, if we round correctly. All right, good. Now, another question you may have is, how much did this help? So delta RSS is going to be this. We started out with 17.46. That's what we had with the null model. And notice the deviance in the left child is 2.20, if we just take 2 decimal places with us. And the deviance of the right child is 0.63. So that would be the improvement due to this split. And so that's going to be roughly 15. So just with that one split, we cut our sums of squares by 14 or 15. So it's quite good. And that shows up on this dendrogram as follows. So we have a left child and we have the right child. All right, well, if we go back to what I said, what we're going to do is we found our best split. It maximizes this change in sums of squares. If our stopping criteria is met, we're going to exit. Well, let's just say it's not met. So therefore, I'm now going to go build a tree using only the cases in the left bin, so this left child. And so I'm going to take the 19 cases that I had over here, and I'm going to search for another split. So let's go do that. And so what you're going to see is R found another split, which is at 0.63. So 0.63 is about right here. And so we're going to split the data right at that point. Now, what you'll see is that there are 5 cases in the left child, 1, 2, 3, 4, 5. The right cases would have the remaining 14 observations between 0.63 and 2.03. So let's go add this split, and maybe I add it with a red pen. So this becomes my second split. So 0.63, I think, was the place where we were going to chop it. And so you can think about, this is now bin 4, and following R's notation, this is bin 5. All right. And then you could say, well, N4 is equal to 5, N5 is equal to 14. 14, because 14 plus 5 is equal to 19. And then let's just go completely interpret this. This is 0.35. So my y bar here, we could call this y bar 4 is 0.35. and my y bar 5 is going to be 0.77. So somewhere up here, it got a little bit higher. So y bar 5 is 0.77. All right, maybe I could make that a little bit bigger for you, if that helps. All right. Now we could say, well, how much did that help us? And the answer would be, we started out with a residual sum of squares in that left child. So this is the left child of 2.20, and you can see the this left grandchild, if you will. So this would be the left grandchild, has very small deviance, only 0.22. The right child has somewhat larger deviance, 1.34. So the sum of those like 1.5. So we improve things by about 0.7-ish, it looks like. So the way to think about this is this left grandchild. We call this the grandchild of the root. This would be the left child of the left child. And then the right child is sitting over here. Okay, what do we do next? Well, the next thing we would do is, so we've introduced the split. I'm going to recursively call build tree on this left child. So we would pass off these 5 observations to build tree. It would go see if it could split them. It would find a split, but what's going to happen is we're going to run into some stopping criteria. So the stopping criteria that's going to hit is we don't have enough cases. With only 5 cases, we shouldn't be splitting it. And so there's a parameter that you can set that says we're not going to split a node that has that so few cases. So it's going to return. It's going to come back and say, well, I'm not going to do any splits. Then what happens? Well, remember we had called up build tree on these 19 cases, and so it's going to try to split up the observations between 0.63 and 0.22. So it's going to go search that, and lo and behold, it finds a split, and that split is at 1.34. So that's that split right there. So if I come over to my picture, we're going to have a split at 1.34, and you can think about this as now, instead of bin 5, we've split bin 5 into bin 10 and bin 11. And so rather than having this the single line is at 0.77, maybe we go grab an orange marker here. It's going to be higher here, and it's going to be lower here. And we've improved our sums of squares. You can see that the sum of these two sums of squares is roughly, what is that, 0.8-ish, something or other, versus 1.3. So we've reduced our sums of squares by including that split. And you can see how we're very slowly approximating the sine wave with this step function. All right, what would we do next? Well, I would go try to split this, this bin with 8 nodes in it. We wouldn't be able to do it, so we would stop. We would try to split this one over here. We wouldn't be able to do it, so we would stop. What would we do then? Well, remember I've got all of these observations off to the right. So in my picture here, we had 11 observations sitting off to the right. That was bin 3. And we haven't tried to split that yet. So we'll call up build tree and see if we can find a split off to the right. And the answer is, yeah, we can. So we could split things at 2.5. So I'll just introduce a split here at 2.5. And let's go look at our y hat values. So we're going to have a slightly more positive y hat, so minus 0.54 over here, and a more negative y hat on the right-hand side, 0.99. That's negative 0.99. And so we're gradually gradually tracing out this sine wave by doing this. So I now want to just introduce some terms for us that we're going to be using. I've been using these terms already. So this is a tree, and we would call this the root node. in computer science, trees grow down rather than growing up. They usually grow down. So what we've done is we've split the root node into two children. Then we split, for example, the left child into two children. These would be called grandchildren. This would be a great-grandchild of the root node. Let's go see what else I had on this page. Sibling. So we would say that these two nodes are siblings, or these two nodes are siblings of one another. We could use that language. One other set of terms that we need to know is a leaf or a terminal node. So a leaf or terminal node is one that has no children. So you can see that this is not a terminal node because it has two children. Likewise, this is not a terminal node because it has two children. These nodes are the terminal nodes. So it looks like I've got 1, 2, 3, 4, 5 terminal nodes, or 5 leaves in this tree. This number of terminal nodes is going to be our measure of the complexity of a tree. So it's going to tell us how complicated that tree is. Non-terminal nodes are nodes that have at least one child. So these, the root, this node, and this node would all be non-terminal nodes. A binary tree is a tree that has only two types of nodes. So either two children or no children. There are other trees that would, like non-binary trees could have 3 children. And so methods like CHAID allow 3-way splits in addition to 2-way splits. It turns out that's not a very good idea. And the reason is you fragment your data too quickly. And so one of the key insights of Bryman-Friedman-Cart method was only allow binary splits. Another term that you need to know is split. So I've been using this language, but let's define it. It's just a partition of a single predictor variable. So I split my x, for example, at 2.03. So all the values less than that go left, all the values to the right of that go to the right child. Finally, depth is going to be the minimum number of nodes in a path between the root and the terminal node. So let's go count the path. So this would be 1, 2, 3, 4. This tree would have a depth of 4. So I would take the maximum number of nodes in a path. So if I took 1, 2, 3, that's not as big as 1, 2, 3, 4, which is bigger than 1, 2, 3. So the depth of this would be 4. I take the longest path between the root node and a terminal node, and I get the depth. All right, so that's enough for one video. We'll come back in a minute and do part 2 of my tree lecture.